Welcome back to iTech 770 Health IT Databases. This is part B of week 5, the second part of week 5, and we're going to dive into the join operations. This is kind of a complex subject topic, but a very powerful capability. It's important that you understand. So we're going to take our time, we're going to go through it thoroughly with lots of examples. I hope it makes it easier for you to understand and grasp the important concepts. This is one of the most important concepts in SQL, the join operation. If you've ever wondered how we connect the data from multiple tables to get a complete picture of the patient, their encounters, their diagnoses, lab results, this is the introduction to those concepts. This is the lecture that answers that question. Joins are the glue that hold relational databases together. And mastering joins is essential for anyone working, especially in health, the complex area of health informatics. So why do joins matter? Let's start with why. In a well-designed relational database, we don't store everything in one big giant table with lots of rows that have thousands of columns. That would be inefficient and lead to massive data redundancy. Instead, we normalize our data, which we've done earlier in week 2 and 3, which means we split across multiple tables. The patient demographic information lives in the patient table. Lab results are stored in the lab results table. Encounter information including things like vital signs and visit notes, are in the encounters table. This design is very elegant and very efficient, but it creates a challenge. What if I want to see a patient's name alongside lab results? That information lives in 2 different tables. So how do I bring them back together? The answer, of course, is join, the join operations. Joins allow us to combine rows from 2 or more tables based on a related column between them. This is how we reconstruct the complete picture of a patient from normalized data. Before we dive into the join syntax, we need to understand the foundation. Keys, the keys. A primary key, or PK, is a column that uniquely identifies each row in a table. In our patients table, patient ID is the primary key. Remember the rules. No 2 patients can have the same primary key. A foreign key now, or FK, is a column in one table that references the primary key of another table. So in our encounters table, patient ID is a foreign key that points back to the patient's table. Okay, this relationship is what makes joins possible. When we join patients to encounters, we're saying match the rows where the patient ID equals the encounters patient ID. The database engine uses these key relationships to reconnect the data. And this is fundamental to relational database design. And you'll see these relationships throughout our XHealth schema and in every healthcare database you ever work with. Let's look at our XHealth Community Health Center database schema. At the top, we have the patients table with the patient ID as the PK, the primary key. Below that, we have the encounters table. It has its own primary key, the encounter ID. Plus, it has a foreign key, the patient ID, that links back to the patient table. So this is a one-to-many relationship. One patient can have many encounters. Below encounters, we have several child tables. Diagnoses, medications, procedures, and lab results. Each of these has a foreign key linking back to the encounters. So if you want to find all the diagnoses for a patient, you need to go through encounters first. Patient to encounters to diagnoses. This hierarchical structure is typical in healthcare databases and reflects how clinical data is actually generated. A patient comes in for a visit. That creates an encounter, and during that encounter, diagnoses are made, procedures are performed, and laboratory tests are ordered. So SQL provides several types of joins, and choosing the right one depends on what question you're trying to answer. An inner join returns only rows that have a matching value in both of the tables that you're joining. And this is the most common type of join done. Now, a left outer join, usually just called a left join, returns all rows from the left table plus rows that match with the key from the right table. If there's no match, you get null values for the right table columns. Now the right outer join is the mirror image, all rows from the right table, plus any rows that match the key from the left table. Then the full outer join returns all rows from both tables. You'll find nulls in the columns where there's no match on either side. And finally, there's the cross join, which is not used very often, but it returns the Cartesian product. That means every possibility for every row in the left table, you have as many rows in the output table as there are in the right table. So you're going to end up with a lot of rows if either or both of the tables are large. So in healthcare databases, inner join and left join are by far the most common that we'll use. You'll use inner join when you want only records that have related data in both of the tables, and left join when you need to include records that might not have matching data, like patients who have never had a lab test. Look at these Venn diagrams, and I'll give you a hint. There's a mistake in one of them. The left join, that the blue shading should have gone around the full circle, but we'll get into that in just a second. Think of the left circle as table A and the right circle as table B, with the overlapping area representing rows that match both tables. Now for an inner join, you're only going to get output from the intersection where there's data in both of the tables. For the left join, the entire circle is shaded plus the intersection, which is not exactly correct. So you got to, in your mind, think of that as being colored just like the opposite in the right join. They should be parallel. For right join, it's the opposite, the entire right circle plus the intersection. So for full outer join, you get both circles, they're completely shaded, and we get everything from both tables. So cross join, which isn't shown with a Venn diagram because it's conceptually quite different. It's not about matching, it's about combinational mathematics. Every row from A paired with every row from B. You better use it carefully though, because it can produce enormously large outputs. All right, let's talk about the syntax. In the inner join, we select the columns we want from the first table and then inner join the second table on a matching condition. The on clause specifies how the tables relate, typically by comparing a foreign key to a primary key. A few important notes. Inner join returns only rows where the key exists in both tables. If a patient has no encounters, they won't appear in your results table at all. Also, the keyword inner is optional. If you just write join without specifying a type, SQL assumes that you mean an inner join. So you see both styles in production code. I recommend you be more explicit when you write your inner join, just for clarity's sake. Let's walk through a concrete example. Let's say we have a patients table with just 3 patients, P001 John, P002 Jane, and P003 Bob. Our encounters table has 3 encounters, E001, E002, and for patient P001, and encounter E003 for patient 2. Now notice that P003, patient 3, Bob, has no encounters, has no records in the encounter table. So let's look at what happens when we do the joins. When we interjoin these tables on patient ID, what do we get? What do we get? P001, John, appears twice because he has 2 encounter records, rows. P002, Jane, appears once because she has 1 encounter. But P003, Bob, is completely excluded from the results. Why? Because interjoin only returns rows with matches in both tables, and Bob has no matching encounter record. This is crucial for you to understand. If you need to see all the patients regardless of whether they have an encounter or not, you need to use the interjoin is the wrong choice. Here's a practical healthcare query using interjoin. We want to find all patients with their encounter dates and chief complaint. We select patient ID, first name, last name, all from the patient table. And we're going to alias this time. You need to learn how to do alias because it'll keep you from having to key lots and lots of text. It's much more efficient, and it's the policy that most coders use, using an alias. And you'll notice in this code, in this example, it says p.patientid. Obviously the p is going to be for patient, but we haven't defined the alias yet. We don't get a chance to define the p as the alias until we get down into from patients p. So you need to be acclimated to the fact that that the aliases are often introduced later into the code. And then we have the encounter date and chief complaint from the encounters table, which we alias as E. And that's common, just like in Python. You use single letters for aliases often. And so we're going to interjoin on the patient ID. Notice that the table aliases P and E. They make the query much easier to read, especially as queries get more and more complex and the number of tables expands. Now the on clause specifies our matching condition, where p.patientid equals e.patientid. We'll get the same patient linked together. The results will show every patient/encounter combination, but only for patients who actually have encounters. Patients with no visits will not appear. All right, now let's chain multiple interjoins together and see what happens. Look at this query here. This query connects four tables, the patients, encounters, providers, and diagnoses. We want to see the patient name, the provider name, the encounter date, and diagnosis information all in one result set. We start from patients, then interjoin encounters on patient ID, then we interjoin providers on provider ID to get the provider's name, and finally we interjoin diagnoses on encounter ID to get the diagnosis codes and descriptions. So the where clause filters encounters from 2026 onward. This reflects the power of relational databases. Each table stores one type of information, but through joins we can reconstruct the complete clinical picture. The data flows from patients to encounters to providers and finally to diagnoses, all connected by their key relationships. Left join has the same basic syntax as inner join, but the behavior is quite different. Left join returns all rows from the left table, all of them, which is the table in your from clause, plus any matching rows from the right table. If there's no match, the right table columns all contain null. This is essential when you need to include records that might not have related data. For example, if you want to see the patients, including those who have never had an encounter yet, you need to use the left join. With inner join, those patients would be invisible to your query results. Left join. Let's do a visual example. Let's revisit our example with a left join query. Let's use the same patient table with P001, 2, and 3. Same encounters table with P001, 2. But now we're going to use a left join. When we use the left join, the results include all 3 patients. P001, 2 appear with their encounter IDs, just like before. But now P003, patient 3, Bob, also appears in our results, but with a null in the encounter ID column. This null informs us that Bob had no matching encounter record. He's in the patients table, but has not yet been seen in an encounter. So here's a key insight for you to understand. Look at that example very carefully. Be sure that you understand it before you proceed. Left join preserves all rows from the left table. So if we're using the patient table, we're going to have a row for every patient. And we'll fill in nulls where there's no match. This lets you identify gaps in your data, like patients who haven't been seen, or in another example, you might find that providers who have not been assigned any appointment data. Let's talk about our XHealth example again with the left join. We're going to select the patient information, see all the data we're going to get, the patient ID, first name, last name. Then we're going to get the data of the encounter, because we're going to left join with encounters. And this query looks almost identical to our inner join example, but the results are going to be different. Look carefully. With the left join, every patient's going to appear in our output results, even those who have no encounters. But for patients without encounters, the encounter date column will have a null. And this is how you can identify patients who might need some special outreach because they don't have an active appointment. They're registered in your system, but they actually have never been seen. So in a value-based health environment, these are exactly the patients you want to find and engage and recruit. Here's a powerful pattern that you'll use often. The left join combined with is null in the where clause. Look at this carefully. This query finds all the patients who have never had a lab test. We left join patients to the lab results on the patient ID, and this gives us all patients with nulls for those who have no lab records. Then we add where lab result is null, and this filters to only the rows where there was no match in the lab results table. This pattern, left join plus where the right table key is null, is a standard way to find orphaned or missing records. Use it often to find patients without encounters, or encounters without diagnoses, or providers without appointments, or any other type missing relationship in your database. This is a pattern you will use very commonly. All right, let's move on to the right outer join syntax. Of course, this is the mirror of the left join, and it returns all the rows from the right table plus matching rows from the left table. In practice, right join is very rarely used because you can always get the same results by just switching which table you call left and which one you call right. And that's, in practice, what we usually do. But you still need to learn how to do the right outer join. Let's look at these 2 examples on the slide. The right join query and the left join query with swapped tables produce identical results. And most developers find using left joins more intuitive because we kind of naturally read from left to right. So the all rows table being mentioned first makes the query a little bit easier to read and understand. My recommendation would be to stick with the left joins and just put your all rows table first. But you need to be able to read this code and understand that the right join, because you may find it in some code that you're asked to review. Let's use our healthcare example to look at the right join. Here's a scenario where you might see right join used. We want all providers, including those who haven't had any encounters. So we start with encounters, the from encounters, and right join providers, and this ensures that all providers will appear in our output. Then the use case here is to identify the providers who haven't seen any patients. Maybe they're a new hire or just getting credentialed or specialists waiting for some referrals. The null values in the encounter columns reveal these gaps. Again, this could be rewritten as a left join with providers as the first table. So either approach works. It's just a matter of style and readability. Now let's look at the full outer join, the syntax. It returns all rows from both tables. If a row is in the left table has no match in the right table, you'll get nulls for the right columns. If a row in the right table has no match in the left table, you get nulls for the left columns. And if there's a match, you'll get data in the columns from both. This is less common than inner or left join, but it is invaluable for data reconciliation purposes. When you need to compare two data sources and find discrepancies on both sides, the full outer join is the tool you need. So let's try a specific example. Let's trace through a full outer join with some very simple data. The left table has IDs 1 and 2 with values A and B. See that? The right table has IDs 2 and 3 with values X and Y. ID 2 exists in both of these tables. IDs 1 and 3 exist in only one of the tables. The full outer join result has 3 rows. ID 1 shows the value A from the left and null from the right because there's no ID 1 in the right table. Now ID 2 shows B and X because it exists in both tables. Then ID 3 shows null and Y because there's no ID 3 in the left table. So you see the 3 rows that are the result of this join happens because you're going to have a row from each of the tables, regardless of whether there's data in the other table. So this is a comprehensive view that shows you exactly what exists in each source and where the overlaps and gaps are by identifying the nulls. We rarely use the full outer join, only in very rare examples, but let's talk about at least one situation where it might be used. We might want to find the unmatched records between the electronic health record system and our lab system. So trying to reconcile patient records between the two systems to find out if there's some records that may have gotten lost. So you're trying to find patients that exist in one system but not in the other. We full outer join the EHR patients and the lab system patients on the patient ID and then filter to where either side is null. So the results show 2 types of discrepancies: patients in your EHR with no lab system record and patients in the lab system with no EHR record. Both are problems that should be investigated. This type of reconciliation query is essential during system integrations when we're merging lots of data with data migrations and sometimes in routine data quality audits. But it's how you ensure that your systems are synchronized and that patients are not falling through the cracks. How about the cross-join syntax? Select columns from table 1, cross-join table 2. What's going to happen? It's going to return every row from table 1 paired with every row from table 2. So if you have 10 rows in table 1 and 10 rows in table 2, you end up with 100 rows. So the one use case for this is to generate all possible combinations. All possible combinations. This can quickly overwhelm your database, so be careful using the cross-join. But here's one use case. Generating appointment slots for scheduling. Suppose we have a providers table and a time slots table, and we want to create a record for every possible combination of a provider and a time slot so the patients can book appointments, find out which appointment slots are available. The query cross-join can join the providers and time slots filtered by a specific date or which providers you're interested in looking at. Let's say we have 5 providers and 8 time slots for a day, we can generate 40 rows representing all possible combinations of appointments and the providers. And this is the seed data for a scheduling system to be sure that all the appointment slots are appropriately utilized. And the key is that we filtered before the cross-join, keeping the input tables small. Never cross-join a full large table without filtering it first, or you end up with a humongous output. All right, let's talk about multiple joins, like chaining tables, connecting 3 or 4 or more tables together. And this is going to happen very often. In real queries, you'll often need to connect more than 2 tables. This query chains 3 joins, the one we're going to look at here. Patients to encounters to diagnoses, and each join adds another table to our result set, following the foreign key relationships. The data flows from patients through encounters to diagnoses. We start with patient information, add encounter information by joining on patient ID, and then add diagnosis information by joining on encounter ID. The where clause filters to recent encounters to limit the size of our output data. You can chain as many joins as necessary, but be aware that performance can degrade with too many joins. If you're joining 5 or more tables, consider whether you can break the query into smaller pieces or create some temporary small tables that process more quickly. All right, let's look at our complete patient view. We want to look at a lot of patient data. This query demonstrates building a complete patient view using multiple left joins. We want demographics, encounters, diagnoses, and lab results for patient number 42. And we want to see the patient even if some of that data is missing. So what do? We use the left join throughout, ensuring that we'll see the patient record regardless of what related data exists or does not exist. If the patient has no encounters, we will still see their demographics. If they have encounters but no diagnoses for some, we will still see those encounters. The nulls will help tell us what's missing. This is a common pattern for patient dashboards and longitudinal views. You want the complete picture, including what's absent, not just what's present. Table aliases. Let's talk about our best practices for developing aliases. And you can see the confusion and why it's better to use aliases. It makes your code much clearer. In red, we have the code without the aliases, and it's quite verbose. On the right side, you have it in blue. You have a cleaner code by using the aliases, P for patients, E for encounters. And that allows you to shortcuts that is still very readable, but much less key punching, much less typing. You always want to employ meaningful and useful abbreviations. It's very common to just use the first letter or the first couple of letters if you have some redundancy. Like P for patients is commonly used, or E for encounters, PR for providers, D for diagnoses, L for lab. Whatever convention you choose, be consistent about it and use it across all of your queries. Let's look at another permutation of the join conditions rather than just when something equals something beyond equality. Most joins do use equality conditions when one key equals another key, but sometimes SQL allows us to use more comparisons in the join clause. Like this query here uses between to match patients to age-based screening recommendations. So instead of on p.patient ID equals ar.patient ID, we use on p.date of birth between a range, and this matches each patient to the age range that contains the date of their birth, returning the appropriate screening recommendations for appropriate patients based on a calculated age. You can use any of the available comparison operators in a join condition, such as less than or greater than. We can even use that like clause for pattern matching with wildcards, or you can use complex expressions. The key is that the condition must evaluate to true or false for each potential row pairing. What about self-join, a table that joins itself? A self-join is when a table is joined to itself, and this query finds potential duplicate patients by looking for records with the same last name or the same date of birth. We treat the patient's table as two separate tables by giving it two different aliases. So we P1 and P2, even though they're both the patient table, they've given separate aliases so that we can do the comparison to separate the data. The join condition matches on last name and date of birth. The condition P1.patient ID less than P2.patient ID prevents duplicate pairs. Without it, we'd get both A and B and B and A for each match, plus A and A for every record. So you have to be careful. Self-joins are essential for finding duplicates, and also for building hierarchies like organizational charts and comparing records within the same table. The aliases are required because SQL needs to distinguish between the two instances of the same table. Joins and aggregate functions. Joins combine naturally with aggregate functions like count, sum, and average. This query, this example here, counts the encounters for each patient. We left join patients to encounters and group by patient information. The count function tallies encounters for each patient. Using left join ensures patients with 0 encounters still will appear in the results, but with a count of 0. Notice that every non-aggregated column in select must appear in group by. We're selecting patient ID, first name, and last name, so all three must be in the group by clause. This is a common source of coding errors. Always check that your group by matches exactly, precisely your select clause. One thing you need to take into account is the performance of your code. Joins can be very time-consuming. Processors take a lot of processing power, so we need to think about how the data is really constructed to understand what we're asking the system to do, especially when you have large tables. So here are some key concepts. Indexing join columns provides the most dramatic improvement. So what does indexing mean? This means that in your table setup, you've created keys that have indexing calculated to allow them to get to search through the data through that key, finding the matches much more quickly. They can use hash functions and other tools to be able to get through finding the matches much more quickly. So that could be a dramatic improvement in your processing. So you always create indexes on the foreign key columns. The database can use these indexes to find the matching rows much more quickly instead of having to scan individually row by row by row, which can be very time-consuming and laborious. Also, the order that you do your joins can affect performance. As a general rule, start with the smaller tables or tables that you're filtering heavily, and this will reduce the number of resulting rows before you start doing more processing that are joined at each step. So try to be selective in your select clause. Avoid select star. Remember, we've talked about that before, not to use star. Be more specific about which columns you need. Only retrieve the columns you actually need, and this will reduce the data transfer across your database. And also filter early with where clauses. If you can reduce the number of rows before you do the join itself will process much faster. If a join query is running slowly, the first thing to check is whether indexes exist on all the foreign keys, on all the columns you're using in the on clause. Let's talk about mistakes. that I see quite frequently. Missing the on clause creates an accidental cross join, producing a massive Cartesian product. Always specify your join condition. Using the wrong key columns produces incorrect matches. Verify your foreign key relationships before you write your query. You can forget table aliases when the same column names exist in multiple tables, causing some ambiguity and making column errors. Be very consistent in your choice of the alias text. And also another common mistake is using inner join when you need a left join, which silently drops records from your results. This is probably the most common mistake I see. Always ask yourself, do I need all the records from one table or only the ones that have matches? Another common mistake is chaining too many joins, which can significantly degrade your performance. If you're joining more than 5 or 6 tables, consider trying to break the query into steps and producing intermediary temporary tables or subqueries. All right, this reference table maps common healthcare questions to the appropriate join type. Patients with their encounters. You can use the inner join. All patients, even without visits, then you have to do the left join. Or finding orphan records, then you need to have the left join plus is null. Complete patient record across multiple tables, you're going to do multiple left joins. To identify duplicates, you're going to do a self join. And system reconciliation, you're going to do a full outer join. So the different types of joins have specific use cases, and it's important that you understand when one or another is appropriate. The key is to match the join type to your business question. Think about what you need in your results. Do you need only matching records, or do you need to preserve all records from one side? The answer will determine the type of join that you need to employ. When in doubt, I think you should use the left join and examine the nulls, see what you come up with, and then you can change your code if you get more information than you need. Let's do a little practice. Let's transform the data model. Let's recall what we've learned from our course materials and do a practice scenario. We have 3 tables: patients with the demographic data, doctors with their provider information, and appointments as a bridge table linking the patients to the doctors. This is a classic many-to-many relationship. A patient can have many appointments with different doctors. A doctor can have many appointments with different patients. The appointments table sits in the middle, containing foreign keys to both patients and doctors. To answer questions that span these relationships, we need joins. Which doctors has this patient seen? Which patients has this doctor treated? What appointments are scheduled for next week? All these queries require connecting the tables using join. Let's give you an example, finding patient appointments. Let's try to find all the appointments for a patient with the ID 20456. We start from the appointments as our base table because it's the bridge that connects everything. We interjoin doctors on the doctor ID to get the provider details. Then we interjoin patients on the patient ID so we can filter the patient. The where clause filters to patient 20456. The select retrieves appointment, date, notes, doctor name, and specialty. Notice that we're joining patients just to filter by patient ID. We could also filter directly on appointments.patient ID if we know the value. But joining to patients lets us filter by patient name or any other demographic attribute that we would like to use. So look at this code carefully. We're selecting the appointment date, notes, name, specialty, and the appointments are from A dot. We're using that alias, and D for the doctor name for the providers. And we're getting them from appointments, interjoin doctors, interjoin with patients, and the where at the bottom of the code is what selects just the patient that we're looking for. So this query starts from the appointments, joins the doctors, joins the patient, and filters by the patient ID. A great example. Shows you the power. Let's look at another example. Complete appointment view. Show all the appointment details with patient and doctor information. This query creates a complete view of all the appointments with patient and doctor information, and we will join all three tables: appointments to patients and appointments to doctors. There's no where clause because we're not looking for just a single patient. So we get every appointment in the system. The result shows the patient name, patient date of birth, doctor name, the doctor's specialty, the appointment date, and the notes, like the chief complaint might be in there. This is the kind of query you might use for a scheduling dashboard or an appointment report. Note that I used join without the inner keyword. Remember, plain join defaults to inner. Both styles are acceptable, but be consistent in your coding. Well, let's summarize what we've done today, this part of week 5, the second part of week 5. Let's summarize the different join types and when each is appropriate. The inner join, when you need matches in both tables. Inner join means you want to have data in both tables to get a row in the output. Left join, when you need all the records from the first table plus any matches. The right join, when you need all the data from the second table. Though left join with swapping the tables gets the same results and is more commonly employed. Full outer join, when you need everything from both tables. And cross join, when you need all the possible combinations. We use that self join when we're comparing records within the same table and trying to find relationships between data within records within the same table. So the key takeaways to remember is the inner join is your default for most queries. The left join is essential for finding missing data and building complete views. Always use table aliases to improve your readability. And index your join columns for performance. Be sure that the foreign keys are indexed in your database. Always match your join type to your business questions. All right, so what are we going to do next? What's going to happen from here? We're finished the week 5 part B. If you need to review it, play it again, or if you have questions, contact me. The next part of week 5, we're going to step back from SQL and the syntax we've been talking about in coding and look at the bigger picture. How do databases connect to the broader healthcare ecosystem? We're going to explore interoperability, including TEFCA, FHIR, and the exchange landscape. We'll also profile the major electronic health record vendors, Epic, Oracle. Then understanding interoperability is essential because your SQL skills don't exist in isolation. You want to be able to be a data analyst. You want to help your organization, your entity, be able to find specific populations, subpopulations, doing queries. So you have to understand SQL. The queries you write operate on data that flows between systems. So you have to understand the flow, and then it's going to make you a much more effective and powerful health informaticist. So please review Part 5A on the data manipulation operations and complete all of your outstanding assignments, and I will be ready to give you Week 5 Part C shortly. Look forward to seeing you.